And as one final step, we could go ahead and reduce y squared times x over y as y squared and y cancel out so that we're left with y times x. If we choose to do that, that just makes it a little bit easier to work with in the event that we actually need to go back and plug in numbers. With that said, we can look at another example, and that other example will be very much the same, except now x is the variable. Now, while this looks very complicated, keep in mind that y is the constant. So you have a number squared and then natural log of a number. That's just a number. That's a constant. And so I can go ahead and rearrange these terms to bring the constants to the forefront, shove them forward. And so this is going to be the partial derivative with respect to x of constant squared times the natural log of a constant times x. Okay, so that right there, because we're treating y as the value that is not changing, that is constrained to a value, and x is the variable. Now, so we have, again, a similar problem like 6 times x to the first power. If that's a constant times x to the first power, its derivative is simply 6. So while taking the derivative of that with respect to y requires the product rule, here we don't have a product of functions of the variable. We have a constant times the variable, and as up here, our constant was 6, our constant down here is y squared natural log of y, and so we're left with is y squared natural log of y. Whoops. And now we could take a look at another example where we're going to treat w as the variable, and we're going to treat y as the constant. Okay, so y is in numbers. This is like taking the derivative of 5w over 3 to the w. Okay, well, if that's the case, then I have a quotient, and I have to use the quotient rule since I have a power function and an exponential function in the numerator and denominator respectively. So that's a constant, and so I need to now set up my quotient rule, which is f is equal to yw, or constant times w. Well, what's the derivative of the constant times w? It's just the constant. And then g is what's in the denominator. That's 3 to the w power. And g prime, well, that's the derivative of a exponential function, which is the natural log of 3 times 3 to the w. And I can put this together, f prime g minus f g prime over g squared. So the derivative ends up being y times g, which is 3 to the w, minus f g prime, which is y times w times g prime, which is the natural log of 3 times 3 to the w, all over the denominator squared, or g squared, which is g is 3 to the w, and 3 to the w squared is that. And that is all. We have completed that step. Okay, chain rule, last rule, and I promise we're done. I know this is a lot of stuff to take in, but the chain rule basically tells us that, if you recall, that if I have a function within another function, then the derivative is the derivative of the outer function with the inner function plugged in, times the derivative of the inner function. So let's see how this rule works, and in the next slide I'll present a way of thinking about it. I call it the stuff approach, and or maybe I don't call it that, but somebody else called it that, and I like it. So let's try this out. So here it's kind of a little bit more clear. I want to think in terms of f and g. I want to be thinking about whether I have a power or exponential or potentially logarithmic function. So f, if you notice, the outer function is the natural log. The inner function is a quadratic function, which involves power rules. So what I want to do is I want to reduce this function into something that I can differentiate. So what I'm going to call f, I'm going to let f equal the natural log of g. Now g is just the stuff inside the parentheses. Okay, so what's the derivative of the natural log of g? Well, it's 1 over g. Okay, and then that means g is going to be what's inside of the function, which is x squared plus 2x, and the derivative of that is 2x plus 2 by using the power rule on either term, on both terms. Now, the chain rule says you're going to take the f prime function and plug in the g function. Okay, so f prime is 1 over g, and g is x squared plus 2x. So what this is going to look like is f prime of g of x is 1 over x squared plus 2x times the derivative of the inside, which is 2x plus 2. In another example, here I have what I want to be looking for is where the variables are. So here I have variables inside the parentheses. So this is very similar to a power rule like x squared. Okay, so my outer function is, in this case, g squared. It's got guts. I like to think that g stands for guts. I've got guts that contains variables to the second power. The derivative of g squared is 2g. Here's where it gets tricky because we have g prime, right? So maybe we've just got to keep track of which g we're talking about. In this case, g is the guts, but g prime is just part of the. No, I'm sorry. We're okay. So g is take that back. Pretend like I didn't say anything. G is the inside, the guts, which is 2x plus 3, and g prime is the derivative of the guts, which is just 2x plus 3. That's a linear function. Its slope is 2. So I put this all together, f prime with g of x plugged in. So f prime is 2g, and g is 2x plus 3 to the first power. And the derivative of the guts is just 2, which is g prime. And I'm done. And here, same idea, except here, if I look at this, I see 2 to the guts. I see 2 to a power, which looks much like an exponential function. So my guts in this case are the exponent, which is x squared plus 3x. So f is going to be 2 to the g power. F prime, well, that's the derivative of a logarithmic exponential function, which is the natural log of 2 times 2 to the g. And g is, well, what is the guts? The guts is the x squared plus 3x. And g prime is 2x plus 3. Chain rule says f prime, which is the natural log of 2 times 2 to the guts. Well, what is the guts? The guts is x squared plus 3x times the derivative of the guts, which is 2x plus 3. So it's multiplied by all of that there. In this problem, it requires a little bit of rearranging. Square roots are not really friendly to work with when you're dealing with functions. So this is really 2x to the 1/2 power. Okay, well, again, I see guts to the 1/2, something that involves a variable to the 1/2 power. That reminds me of the power rule. I've got a variable down here, and I've got a constant in the exponent. So I have something of the form g squared. F prime would be, power rule on that is 2g. G, the guts, is actually 2 to the x. And g prime is the derivative of the guts, which is the natural log of 2 times 2 to the x. I put this all together. So f prime with g of x plugged in. Okay, f prime is 2g. Well, g is 2 to the x. And that gets multiplied by the derivative of the guts, which is the natural log of 2 times 2 to the x. Okay, so that's a way of taking a function, breaking it up, and then putting it all back together. So basically what we've done is we've decomposed the function, and then we've recomposed it into its derivative form. Now I like to think of this as the stuff approach. So stuff, to me, this is maybe a simplified form, but stuff is anything that involves a variable. Anything that involves a variable. Okay, so for example, here I have the derivative of the natural log of stuff. Natural log of stuff. Well, what's the natural log of stuff? The natural log of x, let's say. Well, it's equal to 1 over that stuff. But according to the chain rule, the stuff is really the guts. So I've got to multiply it by the derivative of that stuff. So I'll call it stuff prime. Okay, well, what is 1 over stuff? Well, 1 over stuff is 1 over x squared plus 2x. And the derivative of stuff, well, the stuff is what's in the parentheses here, which is 2x plus 2. So that gets multiplied by 2x plus 2. Same idea here. I've identified my variables. That's really something I could reduce to the derivative of stuff squared. And the derivative of stuff squared is 2 times stuff. But according to the chain rule, I have to multiply that by the prime of stuff. Okay, let's write that out. 2 times stuff, which is 2 times 2x plus 3. And if you notice that we've really just performed the power rule here, we've dropped the power down, reduced the power by 1, but then we've got to multiply it by the power, the derivative of stuff, which is 2. And that's the exact same, these are the exact same answers we're getting from the previous page. Here, my variable identification is in the exponent, so I've got the derivative of 2 to the stuff. Okay, derivative of an exponential is the natural log of the base times 2 to the stuff times stuff prime. And that's going to be the natural log of 2 times 2 to the stuff, which is x squared plus 3x. Stuff prime is 2x plus 3. And again, you'll notice we get exactly the same derivative by doing it that way. Final problem. This is the derivative of stuff to the 1/2. Square root is the same thing as the 1/2 power. Okay, my stuff is identified here because it contains a variable. It's 2 to the x. And the derivative of stuff to the 1/2 is 1/2 stuff. I don't think I took the derivative correctly in the last problem, but 1/2 stuff, subtract 1 from the exponent, which is negative 1/2, times stuff prime, and stuff prime, 1/2 times 2 to the x to the negative 1/2 times stuff prime, and stuff prime is the derivative of 2 to the x, which is the natural log of 2 times 2 to the x. So that's kind of the stuff approach to the chain rule. It makes it a little bit easier, I think, mathematically. So the thing that I missed here was I actually wrote g squared instead of g to the 1/2. So let me go back and change that. But we end up getting the same answer. One approach is just a little bit more mathematical, and the other approach is more kind of trying to do things a little bit more intuitively. So we get the same answer here as we do on the next slide. Okay. So now we can return to our function here, which was the compound interest formula, and this was reduced to just 2 variables, r and t. And so now I want to ask the question, compute these 2 things and explain what this means to an investor. Okay, well, again, this is just another way of saying we want to take the partial derivative of a with respect to r, and the partial derivative of a with respect to r, and the partial derivative of a with respect to t. Before I plug in any numbers, I'm going to take the derivatives. So I'm going to do the second, this component first. I'm going to do this one first because it's a little bit easier. So what I have is I have 100, and I'm treating r as a constant. So if r is a constant, this whole thing right here is a constant. And then what I have up here is I have the variable, but I have a function of the variable, so I'm going to call this stuff. So I have 100 times constant to the stuff. So if I take the derivative of that, okay, well, that's an exponential function. So 100 times the natural log of the constant times constant to the stuff. But now I have something other than, I have something other than just t in the exponent, so I have to use the quotient rule, or I mean the chain rule, apologize. And so I have to multiply that whole thing by stuff prime. Let's put it all together. So that means I have 100 times the natural log of the constant. Well, the constant is everything that's in parentheses because r is being held fixed. So that's 100 times 12, or if we want to write it, I guess we could say 1200, to the stuff, which is 12t, times the derivative of stuff. Well, the derivative of 12t is just 12. And I am done. That's the derivative of a with respect to t. Now, if I treat r as the variable, what I've got here is t is being held constant. So that means I have 100. Now, it's not just 100r to the constant power. It's 100 times a function of the variable. I have 100 times stuff to the constant. Okay, well, what do I do when I take the derivative of something like that? Well, first of all, this is like a power rule. So I drop the constant down and I subtract 1 from the power. So that means I'll have 100 times the constant times stuff to the constant minus 1 times stuff prime. And in my case, that's going to amount to 100 times the constant, which is, in this case, 12t, that's the exponent, times stuff, which is 1